In this video, I'll talk about the mechanisms with fast initial equilibrium. It's also called pre-equilibrium approximation. It's an important topic in upper division physical chemistry, but I will only give you a brief introduction to this very complex topic. So first, let's review reversible reactions and chemical equilibrium. So let's say the reaction from A to B and the reaction from B back to A take place simultaneously. And then we put a double arrow between A and B. We say it's a reversible reaction mechanism. It's not an elementary reaction. It's a mechanism that consists of two reactions, two elementary reactions. One is from A to B, the other is from B back to A. In this case, the concentrations of A and B will eventually reach equilibrium. Okay, they can be different, but when I say chemical equilibrium, that means the concentration of A and B will never change after this reaction reaches equilibrium. And why is that? Well, at equilibrium, the forward and reverse reactions are still going on, but the forward reaction rate, this Kf times A, is equal to the reverse reaction rate, Kr times B. Alright, so that's why it's called a dynamic equilibrium. The forward and reverse reactions are still going on. It's just the rates of the forward and reverse reactions are exactly the same. Now let's talk about this more complex mechanisms that may involve three elementary reactions. So first, from A to B, that's the forward reaction. You have K sub F here, and then from B back to A, we say the rate constant is K sub R. All right, and then let's add one more elementary reaction. Let's say this B can slowly be converted to C, and C is our desired product. We're trying to get C, and we're interested in how fast this C is produced. Okay, now, if this reaction rate, K sub slow, from B to C, is much smaller than Kf and Kr, so this rate constant is much smaller than Kr and Kf, and then we can assume A and B are always at equilibrium. It may sound strange, so look at this. We have A converted to B and B converted back to A, but now we have a third reaction. Only if the third reaction is slow enough. The third reaction from B to C is so slow that even if this B is slowly consumed, the reaction from A to B and the reaction from B back to A will quickly re-establish the new equilibrium right after the concentration of B is changed in the third elementary reaction. So again, the third elementary reaction will consume B and produce C. But the consumption of B is so slow that it's going to be compensated really quickly by the fast reactions from A to B and B to A. So that's the reason. All right? And then we say, well, throughout the entire chemical reaction, actually there are three elementary reactions. So throughout the entire reaction mechanism, you have Kf times A is approximately equal to Kr times B. This is an approximation. We are assuming A and B are always at equilibrium throughout the entire reaction mechanism. And then for the production of C, okay, so this is production rate of C. We use R as the production rate. And we have this R equals K slow times B. Why is that? Look at this elementary reaction. How fast is this reaction? It's the rate constant K sub slow times the concentration of B. assuming this is an elementary reaction. Therefore, this is a first order reaction because the coefficient in front of B is 1. Therefore, how fast is this C produced? Well, it's just K slow times B. And now we know B is a function of A. And why is that? It's because, again, we assumed there is always an equilibrium between A and B. So by using this equation, we know B is Kf times A divided by K sub R. So somehow we can replace this B with Kf over Kr times A. Okay, again, this B is approximately, the concentration of B is approximately Kf over Kr times the concentration of A. All right, and why do we do this? Well, it's only because sometimes it's easier to keep track of the concentration of the initial reactant A. So B is actually in between. B is between A and C. So sometimes it's easier to just know the concentration of A. And what if I ask you to predict how fast the product C is produced? And then you can simply use this equation. For general chemistry, you don't have to worry too much about mathematics. I just want you to be able to understand this concept and understand that in some really complex reaction mechanisms, we make approximations like this. And again, this is called Preequilibrium approximation, or in some general chemistry textbooks, it's called mechanisms with fast initial equilibrium. And the fast initial equilibrium is referring to this A to B and B back to A. So this Kf and this Kr are much, much greater than the last K slope.